Pick almost anything in the universe and it's spinning. Earth rotates, the moon rotates, the sun rotates. Every planet in our solar system spins at its own pace. Zoom out, and entire galaxies turn slowly, carrying hundreds of billions of stars with them. Even on Earth, storms spiral, water swirls, and motion naturally curves into rotation. That's not something you'd expect by default. You could imagine a universe where everything just moves in straight lines. No spinning planets, no rotating stars, no spiral galaxies. Just objects drifting without ever turning. But that's not what we see. Instead, rotation shows up so often that it feels built in. And once something starts spinning, it tends to keep going. Not for seconds or minutes, but for millions or even billions of years. So where does that spin actually come from? It's not caused by a single event, and it's not something added later. It comes from tiny imperfections in the early universe and a rule of physics so strict that it never seems to break. A rule that makes sure once spin appears, it can't simply disappear. Start close to home. Earth completes one full rotation roughly every 24 hours. That's what creates day and night. At the equator, you're moving through space at about 1,600 kilometers per hour because of that rotation, even though you don't feel it. Everything around you, air, buildings, oceans, is moving with you, so the motion is invisible in daily life. The moon spins too. It just does it in a way that hides the motion. It rotates once for every orbit it makes around Earth, which is why we always see the same side. This is called tidal locking, but the key point is that it's still rotating. It hasn't stopped spinning, it's just synchronized. The sun rotates as well. It's not a solid object, so different parts move at different speeds. Near the equator, it completes a rotation in about 25 days. Closer to the poles, it takes longer. Even at this scale, rotation isn't optional. It's part of how the system behaves. Now move outward. Every planet in the solar system rotates. Some are fast. Jupiter spins so quickly that it completes a full rotation in under 10 hours, which actually causes it to bulge outward at the equator. Others are slow. Venus takes longer to rotate once than it does to orbit the Sun, and it spins in the opposite direction compared to most planets. But none of them are just sitting still. Asteroids rotate. Many of them tumble in irregular ways because of past collisions. Comets spin as they travel through space, sometimes unevenly as gas jets push on their surfaces. Even small fragments of rock drifting between planets tend to have some kind of rotational motion. Go bigger. Stars rotate. Some spin slowly, like the Sun. Others rotate so fast that their shapes become noticeably flattened, with the equator bulging outward due to the centrifugal effect. In extreme cases, stars can rotate near the limit where they would start losing material from their surface. Then galaxies. Entire galaxies rotate as organized systems. The Milky Way, which contains hundreds of billions of stars, completes a full rotation roughly every 225 to 250 million years. Individual stars orbit the galactic center, all following the same general direction set long ago during the galaxy's formation. And it doesn't stop there. Galaxy clusters, collections of hundreds or even thousands of galaxies bound together by gravity, also show large-scale motions, including patterns that involve rotation and angular movement. At every level you look, small objects, large objects, simple systems, complex systems, rotation shows up again and again. At that point, it stops looking like coincidence. These systems didn't all form in the same way. Planets form from disks of gas and dust. Stars form from collapsing clouds. Galaxies form through the merging of smaller structures over billions of years. The environments are different. The scales are completely different. But the outcome keeps repeating. Things spin. So the question shifts. It's not just why do some things spin, it becomes why is spin so common that it appears almost everywhere we look? And there's another piece to notice. On Earth, spinning usually doesn't last. A coin spun on a table slows down and stops. A wheel eventually loses its motion. That's because energy is constantly being drained away by friction and air resistance. In space, those effects are almost absent. There's no air to push against, and objects rarely experience continuous contact with anything else. So once something starts rotating, there's very little to slow it down. That means spin isn't just common, it's persistent. Something that starts rotating can keep going for millions or even billions of years unless a significant force acts on it. So now there are two clear patterns. First, rotation shows up almost everywhere. Second, once it starts, it tends to last. That combination points to something deeper than coincidence. It suggests there's a shared mechanism behind all of it, a rule that applies across different scales and different types of systems. To find that rule, you have to look beyond the visible motion and focus on what's being conserved underneath it. When we say something spins, it sounds like a simple visual, an object turning around like a wheel or a planet rotating on its axis. That's the version we see, but in physics, that visible turning is just one expression of something more fundamental. Start with rotation in the everyday sense. Earth turns around an axis. A wheel spins. A star rotates. These are all clear examples of objects physically turning. But if you stop at that definition, you miss what actually matters. What physicists care about is angular momentum. Angular momentum is the quantity that describes rotational motion. More importantly, it's what keeps that motion going. If something has angular momentum, it resists changes to its rotation. It doesn't naturally slow down or stop unless something interacts with it. That's why spinning behaves so differently in space compared to Earth. On Earth, rotation fades because of friction. Air pushes against moving objects. Surfaces create resistance. Energy gets converted into heat, so a spinning object gradually loses its motion. In space, almost none of that exists. There's no air, very little contact, almost no continuous resistance. So once an object starts rotating, there's usually nothing to take that motion away. It just continues. But angular momentum does more than just preserve spin. It also controls how spin changes when a system changes. It depends on two things: how fast something is rotating and how its mass is distributed relative to its center. If the mass is spread far from the center, the system carries more angular momentum at a given speed. If that same mass moves closer to the center, the rotation speed has to increase to keep the total angular momentum the same. This is why a figure skater spins faster when they pull their arms inward. They're not adding energy in any obvious way. They're changing how their mass is arranged, and the rotation adjusts automatically. This exact effect shows up everywhere in space. Take a large cloud of gas. At first, it might be huge and barely rotating. The motion could be so small it's almost undetectable. Then, gravity pulls it inward. As the cloud collapses, everything moves closer to the center. The size of the system shrinks dramatically, and because angular momentum has to be conserved, the rotation speeds up. A tiny initial drift turns into a noticeable spin. That's one of the key reasons rotation is so common. You don't need a strong starting motion. Even a slight imbalance is enough. Once gravity begins to compress a system, that small motion gets amplified. Angular momentum also has direction. It's not just about how fast something spins, it also defines the axis and orientation of that spin. Once a system starts rotating in a particular direction, that direction tends to stay consistent. That's why planets in a solar system usually orbit in the same direction. They formed from the same rotating disk of material, inheriting its motion. Changing that direction isn't easy. It usually requires a major event, like a large collision. When we see objects with unusual rotations, like extreme tilts or backward spins, it often means something disrupted them in the past. Up to this point, everything fits within the idea of objects physically rotating. Planets, stars, galaxies, all following the same basic rules. But there's another place where the word spin appears, and it doesn't mean physical rotation. At the level of particles, like electrons, spin is an intrinsic property. An electron doesn't have a surface or a structure you can watch turning, yet it behaves as if it carries angular momentum. It produces magnetic effects and follows strict quantum rules. The term spin was kept because the math resembles rotational motion, but it's not literally a tiny object spinning. Even so, it reinforces the same pattern. Across completely different scales, systems carry properties related to angular momentum. Whether it's a rotating planet or a quantum particle, this idea keeps appearing. So when we ask why everything spins, the real question becomes, why is angular momentum everywhere? And once it appears, why can't it just go away? That leads directly to the rule that explains most of what we see, the conservation of angular momentum. If there's one rule that explains why spin shows up everywhere and why it doesn't just fade away, it's this: angular momentum is conserved. That means once a system has angular momentum, it can't simply disappear. It can move from one object to another. It can change form. It can spread out. But the total amount stays the same unless something external interferes. This isn't a suggestion or a rough trend. It's one of the most reliable rules in physics. Every observation we have, from laboratory experiments to large-scale structures in the universe, follows it. To understand what that really means, go back to something simple. Imagine a spinning bicycle wheel held in your hands. If you try to tilt it while it's spinning, you feel resistance. The wheel doesn't want to change its orientation. That resistance comes from its angular momentum. The motion is locked in unless you apply a force. Now, scale that idea up. When a planet is rotating, it carries angular momentum. There's nothing nearby constantly pushing against it, so there's nothing to remove that motion. It keeps spinning. When a star forms from a collapsing cloud of gas, any small amount of initial rotation becomes part of the system's angular momentum. As the cloud shrinks, that rotation speeds up, but the total angular momentum remains the same. Nothing is being created out of nowhere. It's being redistributed. This is why conservation is so powerful. It doesn't just explain why motion continues, it explains how motion changes. Take a collapsing gas cloud again. At the beginning, the cloud might be enormous, with particles moving in slightly different directions. Maybe there's a tiny overall drift, almost zero, but not perfectly zero. As gravity pulls everything inward, the cloud gets smaller. The distances between particles shrink, and because angular momentum must stay constant, the rotation speeds up. This is unavoidable. Even if the initial rotation is extremely small, as long as it's not exactly zero, collapse will amplify it. That tiny motion becomes a clear, organized spin. And here's the key detail. Perfectly zero angular momentum is almost impossible. It would require every particle in the system to be arranged and moving in such a precise way that all rotational motion cancels out exactly. In a real, messy universe, that doesn't happen. So almost every system starts with at least a little angular momentum, and once it's there, conservation makes sure it stays. This also explains why rotation organizes systems into specific shapes. As a collapsing cloud spins faster, it can't keep falling inward equally in all directions. The rotation creates a kind of outward effect perpendicular to the axis of spin. Material spreads out into a disk instead of collapsing into a perfect sphere. That's why stars often form with rotating disks around them, disks that later become planets. The same principle applies on larger scales. Galaxies form rotating structures instead of random chaotic clouds because angular momentum channels motion into organized patterns. Conservation doesn't just preserve spin, it shapes the structure of the universe. Another important point is that angular momentum can be transferred. If two objects interact, they can exchange angular momentum. One can slow down while the other speeds up, but the total amount remains the same. This is happening constantly. For example, Earth's rotation is gradually slowing down because of its interaction with the Moon. Tidal forces transfer angular momentum from Earth's rotation to the Moon's orbit. As a result, the Moon slowly moves farther away, and Earth's day becomes slightly longer over time. Nothing is lost. It's just moved. Collisions do the same thing. When two objects collide, they're angular. Momenta combine and redistribute. The result might be a new object spinning faster, slower, or in a different direction. But again, the total is conserved. So when you look at the universe, you're not seeing spin appear randomly. You're seeing angular momentum being preserved, redistributed, and amplified across different systems. That's why rotation is so common. Not because something is constantly making things spin, but because once even a tiny amount of spin exists, the laws of physics don't allow it to disappear. It has to go somewhere, and over time that somewhere becomes planets, stars, galaxies, all carrying the same fundamental property that started as a small, almost unnoticeable motion. So if angular momentum is always conserved, the next question becomes unavoidable. Where did the very first spin come from? To answer that, you have to go all the way back to the early universe. Right after the Big Bang, the universe wasn't filled with stars or galaxies. It was a hot, dense, expanding mix of energy and particles. At large scales, it was extremely uniform. Matter was spread out almost evenly in every direction. But almost is doing a lot of work here. It wasn't perfectly smooth. There were tiny fluctuations, slight differences in density from one region to another. These weren't large structures yet, just small irregularities. But they mattered because gravity responds to even the smallest imbalance. Over time, regions that were slightly denser pulled in more matter. That matter made them even denser, which pulled in even more matter. Slowly, these small variations grew into larger structures. Clouds of gas, then stars, then galaxies. Now here's the key point. Those early regions weren't perfectly still. Even if the universe started out close to uniform, it wasn't perfectly symmetrical in motion. Particles weren't arranged with perfect precision, and their movements didn't cancel out exactly. That means tiny amounts of angular momentum were already present, almost negligible, but not zero. And that's all it takes. As gravity pulled matter together, those small, irregular motions became more important. When material falls inward, it doesn't come in perfectly straight from all directions. There are always slight offsets, slight sideways motions, slight imbalances. Those tiny sideways components are what create rotation. Once matter starts moving inward with even a small sideways drift, it can't collapse straight into the center. Instead, it begins to curve around it. That motion builds into rotation. And because of conservation, that rotation doesn't fade. It grows. As the region collapses, the same angular momentum is packed into a smaller space. The rotation speeds up. What started as a barely noticeable motion becomes a clear spin. This is why spin doesn't need a dramatic origin. It doesn't come from a single event where something kicks objects into rotation. It comes from the fact that perfect stillness and perfect symmetry don't exist in reality. The early universe had tiny imperfections, and those imperfections were enough. There's another layer to this. As structures grew, they didn't form in isolation. Nearby regions influenced each other through gravity. This created what's known as tidal torques, gravitational interactions that can twist and stretch forming structures. These interactions added to the angular momentum of developing systems. So even if a region started with very little spin, gravitational effects from its surroundings could increase it. That means rotation wasn't just preserved, it was also built up through interactions. Over time, these processes shaped larger and larger structures. Small clumps of matter gained rotation as they collapsed. Those clumps merged into bigger systems, carrying their angular momentum with them. Galaxies formed with large-scale rotation because of both their initial conditions and the cumulative effects of these gravitational interactions. So when you look at a spinning galaxy today, you're not seeing something that's suddenly started rotating. You're seeing the result of billions of years of accumulated motion that traces back to tiny fluctuations in the early universe. And because angular momentum is conserved, none of that motion was ever lost. It was just redistributed, amplified, and passed along. This is the deeper answer to where spin comes from, not from a single cause, but from the combination of two facts. The universe was never perfectly still. And once motion exists, the laws of physics make sure it stays. Now take everything from the early universe, tiny irregular motions, small amounts of angular momentum, and the pull of gravity, and zoom in on one of the most important transitions, how a cloud of gas turns into a spinning star. It starts with a region inside a larger cloud, slightly denser than its surroundings. Gravity pulls material inward. At first, the collapse is slow. The cloud is huge, often spanning light years, and the motion is messy. Gas particles move in different directions, colliding, drifting, and interacting. But the collapse doesn't happen in perfect symmetry. Even if the overall motion looks random, there are always slight imbalances. Some parts of the cloud have tiny sideways motions. Some regions pull a little harder than others. These differences are small, but they matter. As the cloud contracts, those small sideways motions become rotation. Instead of everything falling straight toward the center, material begins to curve around it. The inward motion and the sideways motion combine, creating a spiral-like path. Over time, that builds into a coherent spin around a central region. And then conservation takes over. As the cloud shrinks, its size decreases dramatically. What was once a vast, diffuse structure becomes more compact. The distances between particles get smaller, and because angular momentum must stay constant, the rotation speeds up. This is the same effect as the figure skater pulling in their arms, but on a cosmic scale. A cloud that was barely rotating at the beginning can end up spinning rapidly as it collapses into a star. But something else happens at the same time. As rotation increases, it starts to change the shape of the system. Gravity is pulling everything inward, trying to form a roughly spherical object. But rotation introduces a competing effect. Material moving around the center resists collapsing directly along the plane of rotation. So instead of forming a perfect sphere, the collapsing cloud flattens into a disk. This is a critical step. The central region continues collapsing, becoming denser and hotter. That eventually forms a protostar, the early stage of a star. Meanwhile, the surrounding material spreads out into a rotating disk of gas and dust. This disk isn't a side effect. It's a direct consequence of rotation and angular momentum. Without rotation, material would fall straight inward from all directions. With rotation, it organizes into a flattened structure where most of the motion is around the center rather than directly into it. Inside the protostar, the collapse continues. Temperature and pressure rise until nuclear fusion begins. At that point, a star is born. But the spin doesn't stop there. The star retains angular momentum from the original cloud, so it continues rotating. At the same time, the disk around it also carries angular momentum, orbiting the star in the same general direction. This is where planets eventually come from. Dust and gas in the disk begin to clump together through collisions and gravitational attraction. Over time, these clumps grow into planetesimals, then protoplanets, and eventually full planets. And because they form from the same rotating disk, they inherit its motion. That's why most planets orbit their star in the same direction, and why their orbits tend to lie in a relatively flat plane. It all traces back to the rotation of the original cloud. So in one continuous process, you go from a barely rotating cloud of gas to a spinning star surrounded by orbiting planets. No external push is required. No special event has to start the spin. It comes from the combination of small initial motions and the unavoidable effects of collapse under gravity. There's also an important detail about how angular momentum is distributed during this process. Not all of it ends up in the star. In fact, a significant portion remains in the surrounding disk. Some of it is even carried away by jets, high-speed streams of material that shoot out along the star's poles. These jets help remove excess angular momentum, allowing more material to fall inward. Without a way to shed some angular momentum, the collapsing cloud would have trouble forming a compact star. The rotation would prevent material from getting close enough to the center. So the system, naturally, redistributes angular momentum. Some stays in the star, making it spin. Some remains in the disk, driving orbital motion. Some is ejected outward. But the total amount stays consistent. This balance is what allows structure to form, and it explains why rotation isn't just common, it's built into the formation process itself. Every time a star forms, this sequence repeats. A cloud collapses. Small motions turn into rotation. The system spins faster as it shrinks. A star forms at the center, a disk forms around it, and from that disk, planets can emerge. So when you look at a spinning star or a rotating solar system, you're seeing the direct outcome of gravity working together with conserved angular momentum. It's not an added feature, it's the natural result of how matter organizes itself in the universe. Once a rotating cloud collapses into a star with a surrounding disk, the next step is almost inevitable. That disk becomes the birthplace of a solar system. But the key detail here isn't just that planets form, it's how the disk itself behaves. That flat rotating disk is not random. Its shape is directly controlled by angular momentum. When the original cloud was collapsing, material couldn't fall straight into the center from every direction because of its sideways motion. Instead, it settled into orbits around the forming star. Over time, collisions between particles smoothed out chaotic motion, leaving most of the material moving in the same direction, in roughly the same plane. That's why the disk becomes thin and flat instead of remaining a messy, three-dimensional cloud. Inside this disk, everything is orbiting the central star. Each particle, from tiny grains of dust to larger clumps, carries angular momentum. And just like before, that motion doesn't disappear. It gets redistributed through interactions. As particles collide, they don't just bounce randomly. Collisions tend to cancel out motion that goes up and down relative to the disk, while preserving motion that goes around the star. Over time, this process flattens the system even more and aligns the direction of motion. So instead of chaos, you get organization. Now, within this rotating disk, small grains of dust begin sticking together. At first, it's microscopic, tiny particles clumping through electrostatic forces. Then those clumps collide and grow larger. Over time, they form kilometer-sized bodies called planetesimals. At that point, gravity starts to take over. Planetesimals attract more material, growing into protoplanets. These objects continue colliding and merging, clearing out regions of the disk and shaping the structure of the system. All of this happens while everything is still orbiting in the same direction. That's why, in most solar systems, planets orbit their star the same way the star rotates, and they all lie close to the same plane. It's not a coincidence, it's inherited motion from the original rotating disk. Even the direction is meaningful. If the original cloud had a slight rotation in one direction, the entire disk and everything that forms within it follows that same direction. Changing it would require something extreme, like a massive collision or external disturbance. That's why most planetary systems look orderly when viewed from a distance. But it's not perfectly clean. Collisions still happen. Large impacts can tilt planets, change rotation speeds, or even reverse the direction a planet spins. That's why there are exceptions, like planets with extreme axial tilts or unusual rotations. But those are the result of later events, not the original formation process. The default outcome is alignment. Another important detail is how angular momentum is distributed across the system. Most of the mass ends up in the star, but most of the angular momentum doesn't. In our solar system, for example, the Sun contains over 99% of the mass, but the planets carry most of the angular momentum through their orbits. Jupiter alone holds a huge portion of it. This might seem counterintuitive at first. You'd expect the biggest object to dominate everything, including rotation. But because angular momentum depends not just on mass, but also on distance from the center, objects farther out can carry more of it, even if they're smaller. So as the system forms, angular momentum spreads outward. Material closer to the star moves faster but has less leverage. Material farther out moves slower but has more distance, which increases its contribution to angular momentum. This balance helps stabilize the system. It also explains why planets don't just fall into the star. Their orbital motion, driven by angular momentum, keeps them moving sideways fast enough to stay in orbit rather than collapsing inward. So the disk doesn't just create planets, it sets the rules for how they move. And those rules come directly from rotation. What started as a barely noticeable spin in a collapsing cloud becomes a fully structured system, a rotating star, orbiting planets, aligned motion, and long-term stability. All of it traces back to angular momentum being conserved and redistributed during formation. That's why solar systems aren't random collections of objects. They're organized, rotating systems shaped by a process that naturally turns small initial motion into large-scale structure. By the time a solar system has formed, you already have a rotating disk, orbiting material, and a central star. So it might seem obvious that planets would spin too. But the details of how each planet ends up rotating and why they're all different come from a mix of inheritance and chaos. Start with formation. As planets grow inside the disk, they don't form all at once. They build up gradually through countless collisions. Small objects stick together, forming larger ones, which then collide again and again. Each of those impacts carries motion, both straight-line motion and rotational motion. Every time something hits a growing planet, it can change how that planet spins. If impacts come in from random angles, they can tilt the planet, speed it up, slow it down, or even reverse its rotation. Early in a planet's life, these collisions are frequent and often violent, so instead of ending up perfectly aligned or perfectly smooth, each planet develops its own unique spin. That's why planets don't all rotate the same way, even though they form from the same disk. But there's still an underlying pattern because all the material in the disk was orbiting in the same direction. Most collisions happen in ways that reinforce that general motion. So most planets end up spinning in the same direction they orbit their star. This is called prograde rotation. It's not guaranteed, but it's the most common outcome. Earth is a good example. It spins once every 24 hours in the same direction it orbits the Sun. That rotation is partly inherited from the original disk and partly shaped by the many impacts that built the planet. One of those impacts was especially important. Early in Earth's history, a Mars-sized object collided with it. This event is believed to have formed the Moon. That collision didn't just create a satellite, it also affected Earth's rotation, likely speeding it up and tilting its axis. So even something as stable as Earth's spin is the result of a long, chaotic process. Other planets show even more extreme outcomes. Some rotate much faster. Gas giants like Jupiter spin so quickly that they become visibly flattened, bulging at the equator. Their rapid rotation comes from both their formation process and the fact that they accumulated a lot of mass while still interacting with the disk. Others rotate very slowly. Mercury, for example, has a slow rotation that's influenced by its proximity to the Sun. Gravitational interactions over time have adjusted its spin into a stable pattern tied to its orbit. And then there are the outliers. Venus rotates in the opposite direction compared to most planets. This is called retrograde rotation. Instead of spinning the same way it orbits the Sun, it spins the other way. It also rotates extremely slowly. One full rotation takes longer than its year. The most likely explanation is that Venus experienced large collisions or long-term atmospheric effects that altered its rotation. Uranus is even stranger. Its axis is tilted so much that it essentially spins on its side. Instead of rotating like a typical planet, it rolls along its orbit. This extreme tilt likely came from one or more massive impacts early in its history. These examples show something important. Planetary rotation isn't perfectly orderly. It starts with a general direction inherited from the disk, but individual histories can change it dramatically. Still, no planet ends up with zero rotation. Even after all the collisions, adjustments, and interactions, some amount of spin always remains. That's because angular momentum doesn't disappear, it just gets redistributed. There's also another process that can change planetary rotation over time: tidal interactions. When a planet is close to a larger body, like a star or a moon, gravity creates tidal forces that can gradually alter its spin. Over long periods, this can slow rotation and even lock it into a specific pattern. That's what happened to the Moon. It became tidally locked to Earth, always showing the same face. Mercury is partially locked to the Sun in a more complex pattern. So rotation isn't fixed forever, it can evolve. But even when it changes, it doesn't vanish. It gets transferred, adjusted, or synchronized, always following the rules of angular momentum. So when you look at the planets, you're seeing the result of two layers: a shared origin, where everything started with the same rotating disk, and individual histories, where collisions and interactions shaped each planet differently. That's why there's both order and variation. Planets spin because they formed in a rotating system. They spin differently because their histories weren't identical. And through all of it, angular momentum is never lost. It just changes form and direction. If every planet forms from the same rotating disk, you might expect them all to spin in a neat, predictable way. Same direction, similar tilt, consistent speeds. But that's not what we see. Some planets follow the general pattern, others don't. And those exceptions are where things get interesting because they reveal what happened after the initial formation. Start with direction. Most planets rotate in the same direction they orbit their star. This comes directly from the original disk, where everything was moving together. But a few planets break that rule. Venus is the clearest example. It rotates in the opposite direction. Retrograde rotation. Instead of spinning the same way as most planets, it turns the other way, and extremely slowly. One full rotation takes longer than a full orbit around the Sun. That's not something you get from normal formation alone. To flip a planet's rotation like that, something significant has to happen. One possibility is a massive collision early in its history. A large enough impact, hitting at the right angle, can reverse the direction of spin. Another possibility involves long-term atmospheric effects. Venus has a dense, thick atmosphere, and over time, interactions between the atmosphere and the planet's surface, combined with solar tides, may have gradually altered its rotation. Either way, Venus didn't just end up different by chance. Its current state is the result of major changes after it formed. Then there's Uranus. Instead of spinning like a typical planet, Uranus is tilted by about 98 degrees. It's essentially rotating on its side. As it orbits the Sun, its poles take turns pointing almost directly at the Sun, leading to extreme seasonal patterns. That kind of tilt is hard to produce without something dramatic. The leading explanation is one or more massive impacts during its early formation. A collision with a large body could have knocked it over, changing its axis of rotation without stopping the spin itself. So Uranus still follows the rule, it spins, but its orientation is unusual because of its past. Even among planets that rotate in the expected direction, there are big differences in speed. Jupiter spins incredibly fast, completing a rotation in under 10 hours. That speed causes it to bulge at the equator, making it visibly wider than it is tall. Saturn shows a similar effect. These rapid rotations come from a combination of factors: how much material the planet accumulated, how quickly it formed, and how angular momentum was distributed during that process. On the other end, Mercury rotates slowly, taking about 59 Earth days to complete one spin. Its rotation is influenced by its proximity to the Sun. Gravitational interactions have locked it into a stable pattern where its rotation and orbit are linked. This shows another way spin can change over time, not through collisions but through gradual gravitational effects. Then there are smaller objects like asteroids. Many of them don't rotate smoothly at all. Instead, they tumble. Their motion is irregular, constantly shifting. This usually happens because of repeated collisions. Each impact alters their rotation slightly and, over time, the motion becomes chaotic. Even here, though, the rule still applies. They're not losing angular momentum, they're redistributing it in complex ways. All of these examples point to the same conclusion. The original spin of a system sets the baseline. That's why most motion is aligned and follows a general direction. But after formation, individual events, collisions, gravitational interactions, internal processes can reshape how that spin looks. They can tilt it, slow it down, speed it up, or even reverse it. But they don't erase it. There's no easy way for a planet to end up with zero rotation. To completely cancel out angular momentum, everything would have to balance perfectly in the opposite direction, which almost never happens in real systems. So even the weirdest cases still follow the same underlying rule. They spin because they have angular momentum. They spin differently because their history's changed how that momentum is expressed. And those differences aren't random. They're records of what those planets went through. So when you see a planet spinning backward or tilted on its side, you're not just seeing something unusual. You're seeing evidence of past events written directly into its motion. Planets aren't the only things that spin. Stars do too. And just like planets, they don't all rotate the same way or at the same speed. Start with something familiar. The Sun rotates, but not as a solid object. It's made of plasma, so different parts move at different speeds. Near the equator, it completes one rotation in about 25 days. Closer to the poles, it takes over 30 days. This is called differential rotation, and it's common in stars. So even within a single star, rotation isn't uniform. Now look beyond the Sun. Some stars rotate much faster. Young stars especially can spin rapidly, sometimes completing a rotation in less than a day. That speed comes from the same process we've already seen. They formed from collapsing clouds, and as those clouds shrank, their rotations sped up. If nothing slowed them down, many stars would keep spinning extremely fast. But something does. Stars interact with their surroundings in ways that can reduce their rotation over time. One of the main mechanisms is called magnetic braking. Stars like the Sun have magnetic fields that extend into space. These fields interact with charged particles, flowing outward in what's known as a stellar wind. As this material escapes, it carries away angular momentum. It's a slow process, but over millions or billions of years, it matters. That's why older stars tend to rotate more slowly than younger ones. They've had more time to lose angular momentum through these interactions. So stellar rotation isn't fixed, it evolves. Another factor is how stars form in the first place. When a collapsing cloud becomes a star, not all of its angular momentum ends up in the star itself. A large portion is left in the surrounding disk or carried away by jets. This prevents the star from spinning too fast. Without that redistribution, the star could end up rotating so quickly that it would struggle to hold itself together. Even so, some stars get close to that limit. There are stars that rotate so fast they become noticeably flattened. Their equators bulge outward because of the strong centrifugal effect from rotation. In extreme cases, material at the equator is barely held in place by gravity. These stars are often referred to as rapid rotators, and they show how far rotation can go when angular momentum is concentrated. Binary star systems add another layer. When two stars orbit each other, they can exchange angular momentum through gravitational interactions. Over time, this can synchronize their rotations, similar to how the Moon became tidally locked to Earth. In some cases, stars can even transfer mass between each other, which also transfers angular momentum. This can spin one star up while slowing the other down. So stellar rotation isn't just about how a star forms, it's also shaped by its environment and interactions. There's also an important link between rotation and what happens inside a star. Rotation can influence how material moves within the star, mixing layers and affecting how energy flows outward. This can impact how the star evolves over time, including how long it lives and how it eventually dies. So spin isn't just a surface detail, it affects the internal behavior of the star. And just like with planets, no star is truly motionless. Even if a star rotates slowly, it still carries angular momentum from its formation. That motion may change over time, but it doesn't disappear. So across stars, you see the same pattern again. They inherit rotation from the collapse of gas clouds. They redistribute angular momentum during formation. They evolve over time through interactions and energy loss, and through all of it, they keep spinning. Different speeds, different behaviors, same underlying rule. Angular momentum is always there, shaping how stars move and how they change over time. If stars spin, then the question naturally extends to something even more extreme. What happens to rotation when a star collapses into a black hole? At first, you might expect everything to reset. A black hole is such an intense object, gravity becomes so strong, space itself is warped, that it feels like normal rules shouldn't apply anymore. But they do. Angular momentum is still conserved. When a massive star reaches the end of its life, it can collapse under its own gravity. In a fraction of a second, its core shrinks dramatically, from something the size of a planet down to something only a few kilometers across. And just like before, when size decreases, rotation speeds up. If the original star had even a modest rotation, that spin becomes incredibly intense during collapse. The same angular momentum is now packed into a much smaller space, so the rotation rate increases dramatically. The result is a spinning black hole. In physics, these are called rotating or Kerr black holes. And they're not rare. Most black holes we expect to find in the universe should be spinning because the stars they formed from were spinning. But here's where things get more extreme. A spinning black hole doesn't just sit there and rotate like a solid object. Its rotation actually affects the space around it. Close to the black hole, space-time itself is dragged along with the rotation. This effect is known as frame dragging. If something gets close enough, it can't remain stationary. It's forced to move in the direction of the black hole's spin. There's a region around a rotating black hole called the ergosphere, where this effect becomes so strong that everything is pulled into rotation. Objects in this region can't stay still relative to distant space. They have to co-rotate. This isn't just a small detail. It changes how matter behaves near the black hole. Gas falling toward a black hole doesn't drop straight in. Instead, it forms an accretion disk, a rapidly rotating disk of material spiraling inward. As this material accelerates and heats up, it can emit enormous amounts of energy, making black holes some of the brightest objects in the universe when actively feeding. Rotation also allows for something even more dramatic: jets. Some spinning black holes produce narrow, high-speed jets of particles that shoot out from their poles at nearly the speed of light. These jets can extend for thousands or even millions of light years. The exact mechanism is complex, but rotation plays a central role. The black hole's spin, combined with magnetic fields in the surrounding disk, helps channel energy outward along the poles. So even in one of the most extreme environments possible, rotation isn't just present. It's powerful enough to shape entire regions of space. There's also a limit to how fast a black hole can spin. If it rotates too quickly, the structure of space-time around it would change in ways that prevent further increase. So there's an upper bound, a maximum spin rate set by the laws of physics. But many black holes appear to be spinning close to that limit, and just like with stars and planets, their spin can change over time. If a black hole absorbs matter from its surroundings, that material can add angular momentum, spinning it up further. If it merges with another black hole, the resulting object inherits the combined angular momentum of both. These mergers have been observed through gravitational waves, ripples in space-time detected when two black holes collide and combine. The final black hole almost always ends up spinning. So even in these extreme events, angular momentum isn't lost. It's carried through the process and shows up in the final object. What makes black holes unique is how visible the effects of rotation become. You can't see the black hole itself, but you can see how its spin affects nearby matter and space-time. The rotation shapes the motion of everything around it, from glowing disks of gas to jets stretching across galaxies. So when you ask whether everything in the universe spins, black holes give a clear answer. Even when matter collapses to its most extreme form, rotation doesn't disappear. It becomes one of the defining features of the object. Now scale everything up to one of the largest structures in the universe, galaxies. A galaxy isn't just a random collection of stars, it's an organized system, and rotation is one of the main reasons it holds that structure. Take the Milky Way. It contains hundreds of billions of stars along with gas, dust, and dark matter. All of it is moving. Most of the visible matter orbits around a central region, completing one full rotation roughly every 225 to 250 million years. That's not fast in human terms, but on a cosmic scale, it's a steady, continuous spin. And it's not unique. Many galaxies show clear rotational patterns. Spiral galaxies in particular make this obvious. Their arms curve outward from the center, tracing the motion of stars and gas as they orbit. That spiral shape isn't static. It reflects ongoing motion, guided by gravity and angular momentum. So how does something this large start rotating? The process goes back to the same ideas we've already seen, tiny initial motions and gravitational collapse, but on a much larger scale. In the early universe, matter wasn't evenly distributed. Slightly denser regions began pulling in surrounding material. As these regions grew, they merged with others, forming larger structures. During this process, gravitational interactions between neighboring regions created torques, twisting forces that added angular momentum. So galaxies didn't just inherit spin from their initial conditions, they also gained it through interactions as they formed. As matter continued to collapse into these growing structures, the same rule applied. As size decreased, rotation speed increased. The system organized itself into a rotating shape. For many galaxies, that shape becomes a disk. Stars and gas settle into orbits around the center, forming a flattened structure similar to a scaled-up version of a solar system. The motion is more complex, but the underlying idea is the same. Angular momentum keeps material moving around instead of falling straight inward. But galaxies are not perfectly simple. Unlike a solar system where most of the mass is concentrated in one central star, galaxies have mass distributed throughout. This leads to more complex rotation patterns. One of the most surprising discoveries about galaxies is how their rotation behaves. If you measure how fast stars orbit at different distances from the center, you might expect the outer stars to move more slowly, similar to how planets farther from the Sun orbit more slowly. But that's not what we see. In many galaxies, stars far from the center orbit at nearly the same speed as those closer in. This creates what's known as a flat rotation curve. The most widely accepted explanation for this is dark matter, an invisible form of matter that adds extra mass to the outer regions of galaxies. That additional mass changes how gravity behaves, allowing those outer stars to maintain higher speeds. So rotation doesn't just reveal motion, it reveals hidden structure. It tells us that galaxies contain more than what we can see. There are also different types of galaxies, and not all of them rotate in the same way. Spiral galaxies show clear, organized rotation. Elliptical galaxies, on the other hand, often have more random motion, with stars moving in many different directions. But even in those systems, angular momentum is still present. It's just distributed differently. And galaxies don't exist in isolation. They interact, collide, and merge with each other. When two galaxies come together, their angular momentum combines and redistributes. The result might be a larger rotating galaxy or a more chaotic structure, depending on the details of the collision. Even in these massive events, the rule holds. Angular momentum isn't destroyed, it's carried through and reshaped. So at the scale of galaxies, the same pattern appears again. Small initial motions grow through gravitational collapse. Interactions add and redistribute angular momentum. Structures form that, reflect that motion. And once rotation is there, it persists. From planets to stars to entire galaxies, the behavior is consistent. Different scales, different details, but the same underlying principle, shaping everything. By now, it's clear that rotation isn't just something objects happen to have. It actively shapes how those objects look and behave. Spin creates structure. Start with something simple. If you take a non-rotating cloud of material and let gravity pull it inward, it collapses into something close to a sphere. That's because gravity pulls equally in all directions. And there's nothing resisting that inward motion. But add rotation, and everything changes. As the cloud begins to spin, material moving around the center resists falling straight inward along the plane of rotation. Gravity is still pulling inward, but now there's sideways motion that keeps material from collapsing directly toward the center. The result is flattening. Instead of a sphere, the system spreads out into a disk. This is exactly what happens when stars and solar systems form. The original cloud doesn't just shrink, it reorganizes into a spinning, flattened structure. That disk shape is one of the most common outcomes of rotation in the universe. You see it in planetary systems, in accretion disks, around black holes, and in spiral galaxies. Different scales, same underlying effect. Rotation also explains why some objects bulge. When something spins quickly, the outer regions experience an outward effect, often called centrifugal force in a rotating frame. This effect is strongest at the equator, where the motion is fastest. So instead of staying perfectly round, the object becomes slightly flattened at the poles and wider at the equator. You can see this in planets like Jupiter and Saturn. Their rapid rotation stretches them outward, making them visibly oblate. Stars can do the same thing. Fast-rotating stars often show this kind of distortion. So spin doesn't just organize systems, it changes their shape. Then there are rings. Rings form when material can't collapse into a single object, but still shares a common orbit. Around planets like Saturn, rings consist of countless small particles, all orbiting in a flat plane. Their motion is governed by the same balance between gravity pulling inward and angular momentum keeping them moving sideways. Without rotation, those particles would simply fall inward. With rotation, they spread out into a stable, disc-like structure. Spiral patterns are another result of rotation. In galaxies, spiral arms aren't solid structures. They're regions where stars and gas bunch together as they orbit the center. The rotation of the galaxy creates these patterns over time, shaping how matter is distributed. Even weather systems on Earth follow this pattern. Hurricanes and cyclones spin because of rotation, both from the Earth itself and from the dynamics of moving air. The same basic idea applies. Motion curves, organizes, and creates structure instead of remaining purely straight or chaotic. What all of these examples show is that rotation isn't just a side effect. It's a shaping force. It determines whether material collapses into a sphere, spreads into a disk, forms rings, or develops spiral patterns. It controls how matter moves, how it distributes itself, and how stable those structures become over time. And it does all of this while following a single rule. Angular momentum must be conserved. So whenever a system forms, whatever angular momentum it has will influence its final shape. That's why the universe doesn't look random. It's full of patterns, disks, spirals, flattened objects, because rotation organizes matter in predictable ways. Without spin, you wouldn't get solar systems like ours. You wouldn't get galaxies with defined shapes. You wouldn't get many of the structures we see at all. So rotation isn't just common. It's one of the main reasons the universe looks the way it does. At this point, it might seem like rotation is inevitable, and in a way, it is. But that raises a deeper question. If gravity pulls everything inward, and if motion could in principle cancel out, why didn't the universe just end up as a set of non-rotating chaotic clumps? Why do we see so much organized spin instead of random motion? The answer comes down to how unlikely perfect cancellation really is. For a system to have zero angular momentum, every single motion inside it would have to balance out exactly. Every particle moving one way would need another particle moving in the opposite way with the same magnitude, arranged so that no net rotation exists. In theory, that's possible. In reality, it almost never happens. The early universe wasn't perfectly arranged. Even though it was smooth on large scales, at smaller scales it had tiny irregularities, differences in density, differences in motion. Those small differences meant that when regions began to collapse under gravity, their internal motions didn't cancel out perfectly. So instead of falling straight inward from all directions, matter always had at least a slight sideways component. That's enough to create rotation. Once that rotation appears, conservation takes over. It doesn't get erased, It gets amplified as the system evolves. So rather than ending up with still, non-rotating clumps, the universe naturally produces systems with organized motion. There's another factor that pushes things away from chaos: interactions. When particles or objects move in completely random directions, collisions tend to reduce that randomness over time. Motion that goes against the flow is more likely to be cancelled out, while motion that aligns tends to persist. This is especially important in rotating disks. As particles collide, they lose energy in directions that move them out of the plane, but they keep motion that goes around the center. Over time, this filters out disorganized movement and leaves behind a coherent rotation. So chaos doesn't stay chaotic for long. It evolves into something more structured. Gravity pulls matter together. Collisions smooth out random motion. Angular momentum preserves and organizes what remains. The result is not disorder, but pattern. That's why we see disks instead of clouds, aligned orbits instead of random paths, and consistent directions of motion within systems. It's also why rotation becomes dominant rather than optional. Once a system has even a small amount of angular momentum, it can't ignore it. That motion shapes how the system evolves. It determines how matter settles, how structures form, and how stable those structures are over time. So the universe didn't choose between order and chaos in a simple way. It started slightly imperfect, and those imperfections were enough. Gravity amplified them, and conservation laws locked them in. Over time, interactions filtered out randomness and reinforced organized motion. What looks like order, planets orbiting in a plane, galaxies rotating in a clear direction, isn't something imposed from the outside. It's what naturally emerges when motion can't be perfectly cancelled and can't be destroyed. So instead of a still universe, you get one where motion organizes itself. And rotation becomes one of the most visible outcomes of that process. Up to this point, it might sound like angular momentum just sits inside an object, locked in forever. But that's not quite how it works. Angular momentum doesn't just stay in one place, it moves. It can be transferred between objects, redistributed within a system, and spread across different scales. And this constant exchange is a big part of why spinning systems evolve instead of staying frozen in their original state. Start with something simple. When two objects interact gravitationally, they can exchange angular momentum without ever touching. The force between them creates small changes in motion, gradually shifting rotation from one object to another. A clear example of this is Earth and the Moon. As the Earth is rotating and the Moon is orbiting, their gravitational interaction creates tides, bulges in Earth's oceans that are slightly ahead of the Moon's position because Earth is spinning faster than the Moon orbits. That offset matters. The gravitational pull between the Moon and those tidal bulges transfers angular momentum from Earth's rotation to the Moon's orbit. As a result, Earth's rotation slowly slows down, and the Moon moves farther away. Nothing is lost. It's just being transferred. This process is extremely slow, but over long periods it changes both objects. The same kind of exchange happens in many systems. In forming stars, for example, a collapsing cloud can't funnel all its material directly into the center if it has too much angular momentum. Some of that motion has to go somewhere. That's where disks and jets come in. The rotating disk around a young star acts as a reservoir for angular momentum. Material in the disk can move outward, carrying angular momentum away from the center, while other material moves inward to form the star. At the same time, jets, narrow streams of material launched along the star's poles, can carry angular momentum out of the system entirely. This helps solve a key problem. Without a way to shed angular momentum, the star couldn't form as compactly as it does. So even during formation, angular momentum is being actively managed. It's not just preserved, it's redistributed in ways that allow structures to exist. Collisions are another major way angular momentum moves around. When two objects collide, their motions combine. The resulting object might spin faster, slower, or in a different direction, depending on how the collision happened. This is how planets get their spins in the first place, and also how those spins can change later. Each impact adds or subtracts angular momentum, reshaping the system over time. In larger systems like galaxies, interactions become even more complex. When galaxies pass near each other or merge, their gravitational fields interact, redistributing angular momentum across billions of stars. Some stars get flung outward, Others fall inward. The overall structure changes, but the total angular momentum is still conserved. Even within a single galaxy, angular momentum can shift between components. Gas clouds can lose angular momentum and fall toward the center, feeding star formation or a central black hole. At the same time, other material moves outward, balancing the system. So rotation isn't static. It flows, it moves between objects, across distances, and through different forms. Rotation, orbit, internal motion, but at every step, the total amount remains the same. This constant transfer is what allows systems to evolve. Without it, everything would be stuck. A collapsing cloud wouldn't be able to form a star. A planet couldn't change its rotation. A galaxy couldn't restructure itself after a collision. Angular momentum would trap systems in their initial state. Instead, the universe has ways of moving it around. And that's why spin isn't just something objects have. It's something that's constantly being reshaped, shared, and redistributed across the cosmos. So far, it might sound like once something starts spinning, it just keeps going forever. And in a perfectly isolated system, that would be true, but real systems aren't completely isolated. There are processes that can slow rotation down, reshape it, or lock it into new patterns. The important detail is that spin doesn't simply disappear. It gets transferred or redistributed. One of the clearest examples is tidal locking. When two objects are close enough, their gravity affects each other unevenly. The side of one object facing the other feels a slightly stronger pull than the far side. This creates a stretching effect, a tidal bulge. If the object is rotating, that bulge doesn't line up perfectly with the other body. It's slightly offset. And that offset creates a torque, a twisting force that gradually changes the rotation. Over time, this process can slow the rotation until it matches the orbital period. That's exactly what happened to the Moon. The Moon rotates once every time it orbits Earth, which is why we always see the same side. It didn't start that way. Early on, it was spinning faster. But tidal interactions with Earth gradually slowed its rotation until it reached this stable state. This is called synchronous rotation. The same process is happening elsewhere. Mercury, for example, is in a different kind of resonance with the Sun. It rotates 3 times for every 2 orbits. This is another stable configuration created by long-term tidal effects. So rotation doesn't always stop, but it can settle into patterns where the motion becomes predictable and locked. Another process that slows rotation is magnetic braking, especially in stars. Stars like the Sun have magnetic fields that extend far into space. Charged particles flow outward in a stellar wind, and as they interact with the magnetic field, they carry away angular momentum. It's like the star is gradually shedding some of its spin. Over millions and billions of years, this causes stars to rotate more slowly. Younger stars tend to spin faster. Older stars, having lost more angular momentum, spin more, slowly. Again, the motion isn't destroyed, it's transferred to the outgoing material. Planets can also experience rotational changes through internal effects. For example, mass redistribution inside a planet, like shifting material in the mantle or atmosphere, can slightly alter its rotation rate. These changes are usually small, but they show that spin isn't completely fixed even without external forces. Collisions can still play a role long after formation. A large impact can change a planet's rotation dramatically, altering its speed or tilt. While these events are less common later in a system's life, they still happen and can leave lasting effects. Even small objects like asteroids can have their rotation changed by subtle forces. One example is uneven heating from sunlight. As an asteroid absorbs sunlight and re-emits energy as heat, it can create tiny forces that gradually change its rotation over time. This effect is small, but over long periods it can significantly alter how the asteroid spins. So spin can evolve in many ways. It can slow down, speed up, tilt, or lock into specific patterns. But through all of these changes, angular momentum is still conserved. If one object loses spin, something else gains it. If rotation slows, the motion is transferred elsewhere, into orbits, into surrounding material, or into escaping particles. There's no simple way for rotation to just vanish, so when it looks like something has stopped spinning, what's really happened is that its motion has been redistributed into a new form. That's why even systems that seem stable or unchanging are still part of a larger exchange. Spin isn't permanent in its exact form, but it's persistent in its existence. It changes shape, moves between systems, and settles into new configurations, but it never truly goes away. Up to this point, spin has meant something you can picture. Planets turning, stars rotating, galaxies slowly swirling. But at the smallest scales, the word shows up again, and this time it doesn't match that picture at all. In quantum physics, particles like electrons, protons, and neutrons all have something called spin. But they're not literally spinning. An electron isn't a tiny solid sphere with a surface you could watch rotate. It doesn't have a size or shape in the classical sense. If you tried to imagine it physically spinning like a planet, the numbers wouldn't even make sense. It would have to rotate faster than the speed of light to match what we observe. So quantum spin is something different. It's an intrinsic property, meaning it's built into the particle itself. You don't get it from motion through space or from something physically turning. It's just part of what the particle is. Despite that, it behaves a lot like angular momentum in the math. Particles with spin interact with magnetic fields. They can be oriented in specific ways. They follow conservation rules, just like larger rotating systems. And they come in discrete values, fixed amounts that can't be adjusted continuously. For example, an electron has a spin value that can be measured in two main states, often described as up or down. These aren't directions in the everyday sense, but they represent different orientations of this intrinsic angular momentum. This becomes especially important in how particles interact. Spin plays a role in the structure of atoms. It affects how electrons arrange themselves around a nucleus, which in turn determines the chemical properties of elements. It also underlies phenomena like magnetism, where the alignment of many particle spins creates large-scale magnetic effects. So even though quantum spin isn't literal rotation, it still carries the same kind of influence. It shapes behavior, it follows conservation laws, and it appears everywhere. That's the interesting connection. At large scales, spin comes from motion, objects physically rotating through space. At small scales, spin is built in, not derived from motion. But in both cases, it behaves like angular momentum. It resists change. It follows strict rules, it has measurable effects, and it can't just disappear. So while quantum spin doesn't directly explain why planets or galaxies rotate, it reinforces a deeper pattern in physics. The universe seems to favor quantities that behave like angular momentum, whether it's a star spinning in space or an electron carrying. Intrinsic spin, the same kind of structure appears again and again, something that encodes rotational behavior, follows conservation rules, and influences how systems evolve. So the idea of spin isn't limited to visible motion. It shows up at every level, even where motion as we normally understand it doesn't apply. And that makes the bigger picture clearer. Rotation isn't just a feature of large objects. It's part of how the universe is built, from the smallest particles to the largest structures. So after seeing spin show up everywhere, from planets to galaxies to even particles, it's natural to ask, is there anything in the universe that doesn't spin at all? In theory, yes. An object could have zero angular momentum. It could be perfectly still, with no rotation and no tendency to rotate. Physics allows that, but in practice it's incredibly rare. To have absolutely no spin, a system would need to be perfectly balanced. Every bit of motion inside it would have to cancel out exactly. Every particle moving one way would need another particle moving the opposite way with the same magnitude, arranged so that there's no leftover rotation. That kind of precision is almost impossible to achieve in a natural setting. The universe doesn't build things with perfect symmetry. From the very beginning, there were small irregularities, tiny differences in motion and density. As structures formed, those imperfections got amplified, not erased. So most objects inherit at least a small amount of angular momentum. Even if something looks like it's not spinning, that doesn't mean it truly has zero rotation. Take a distant cloud of gas. It might appear still because its rotation is extremely slow or spread out over a large area. But if you measure it carefully, there's almost always some degree of motion. The same goes for stars that rotate very slowly, or galaxies that don't have a clear disk structure. The motion might not be obvious, but it's there in some form. There's also an important detail about reference frames. Rotation isn't always absolute in the way we intuitively think. You measure it relative to something else. An object might appear non-rotating in one frame of reference, but rotating in another. In physics, what matters is whether there's angular momentum relative to the system you're analyzing. And in most real systems, there is. Even objects that seem locked can still be part of a larger rotational system. The Moon always shows the same face to Earth, so it looks like it's not spinning. But it is rotating, just in sync with its orbit. From a different perspective, that motion becomes obvious, so apparent stillness can be misleading. There are also systems where motion is highly disordered rather than organized. Elliptical galaxies, for example, don't have the clean, flat rotation of spiral galaxies. Stars move in many different directions, creating a more chaotic structure. But that doesn't mean there's no angular momentum. It's just distributed in a more complex way instead of being aligned. Even in these cases, the total angular momentum of the system still exists. So the real answer is this. Non-rotation is possible in principle, but extremely unlikely in reality. The conditions required are too precise, and the processes that form structures in the universe tend to create and preserve motion rather than cancel it out. So instead of finding objects that don't spin, what you usually find are objects where spin is subtle, hidden, or distributed in ways that aren't immediately obvious. And that fits the larger pattern. Once angular momentum exists, it doesn't just vanish. It might spread out, change form, or become harder to detect, but it's still there. So the universe isn't filled with spinning objects by coincidence. It's filled with them because avoiding spin is far harder than having it. At this point, all the pieces are on the table. Tiny imperfections in the early universe, gravity pulling matter together, angular momentum being conserved, amplified, and redistributed, collisions, interactions, and long-term effects shaping how systems evolve. Put all of that together, and a clear picture starts to form. The universe was never perfectly still. Even in its earlier stages, there were small differences in motion. Tiny sideways drifts, slight imbalances, nothing dramatic. But those small imperfections were enough. As matter began to collapse under gravity, those motions didn't cancel out. They grew. And once rotation appeared, the rules of physics made sure it couldn't just disappear. That's the key. Angular momentum doesn't allow motion to fade away on its own. It has to be conserved. It can move between objects, change form, or spread across a system. But it always remains part of the story. So instead of a universe where things settle into stillness, you get one where motion builds structure. Clouds collapse and begin to spin. Stars form and keep rotating. Disks appear and give rise to planets. Galaxies organize into rotating systems. At every scale, the same pattern repeats. Not because something is constantly adding spin, but because once even a small amount exists, it gets carried forward and reshaped over time. And there's no realistic way around it. Perfect symmetry is unstable. Perfect stillness is almost impossible. The universe starts slightly uneven, and those uneven conditions are enough to set everything in motion. From there, gravity amplifies it, and conservation locks it in. That's why rotation feels so universal. It's not a special feature, it's the natural outcome of how matter behaves under the rules of physics. Even in the most extreme cases, black holes, merging galaxies, collapsing stars, the same principle holds. Spin might change form. It might become faster, slower, or more complex, but it never truly vanishes. So when you look at a spinning planet or a rotating galaxy, you're not seeing something unusual. You're seeing the result of a universe that couldn't stay still. A universe where motion, once it exists, has to continue, and where even the smallest imbalance given enough time becomes something massive, structured, and impossible to ignore. Subscribe.